Hi, in this video we are going to learn about what is called fuzzy logic, and we will also understand how it is very different from both propositional logic and first order logic. So as this table shows, there can be several different approaches to logic, and they can have different features and different characteristics. So when we talk about propositional logic, we are mainly referring to facts which can have a value of true or false, or it can be unknown also. First order logic, as we now know, is an extension of propositional logic, and in addition to facts, it can have objects and it can have relationships between these objects. And again, the statements in first order logic can be either true or false or unknown. We can now add time to our objects and relations, and then we'll get temporal logic. And here again, the commitment is true, false, or unknown. Now, propositional logic, first order logic, and temporal logic are different in some ways, but largely they are similar in a way that finally the truth value of any given statement is binary, that a statement is either true or it is false. However, in the case of probability theory, the situation becomes slightly different, because we do not exactly know whether a given statement is true or false, but we only know about its probability. For example, if I am tossing a coin, I do not know beforehand whether the coin will turn out to be true or false. After the toss is complete, of course, I know for sure whether it's a head or a tail, but before the toss has been completed, I do not know whether it will turn out to be true or false. And that is how probability theory comes into the picture, because in some sense we are trying to predict what's going to happen about a situation whose full information is not available. So that is when you have a what is called this degree of belief, or what is called the probability of different events happening. Fuzzy logic is somewhat different from probability theory. There are some similarities, but there are some important difference also. The primary similarity, of course, is that like probability theory, in fuzzy logic also we do not have a clear binary truth value of 1 or 0, but we have fuzziness. However, the important difference is that in probability theory, a given statement is either true or false, and all that we are assigning to it is the probability of the statement being true. However, in the case of fuzzy logic, the statement itself is neither true nor false, but somewhere in between. For example, if I say that the height of Eiffel Tower is 800 meters, the statement is either true or false, and so I can deal with it either using first order logic or probability theory or whatever, because there is a precise number of height given which is verifiable. However, if I say that the Eiffel Tower is a very tall building, now what will you say? Is it true? Is it false? It is somewhere in between, because very tall does not have a specific definition in mathematics. 800 meters is specific, you can verify whether that is true or false, but when you say very tall, that is not very specific. So these kind of statements, which are inevitable in our English language, they are dealt with using this framework of fuzzy logic, when the statement itself cannot be put into a binary category of true or false, and there is some subjectivity in the assessment process. So this is the primary difference between probability theory and fuzzy logic, that in probability theory we are still dealing with facts which are verifiable, that at the end of the day it will either be true or false without any ambiguity. But in fuzzy logic, the statement itself is ambiguous, and it is unavoidable because that is the nature of human communication, and that is the nature of the world around us, that there are a lot of things which cannot be established in these binary categories. So we'll see some examples which will make it more clear. So generally, again, going back to our usual way of doing things by what is called a rule-based methods. So these methods of, carrying out inferences have certain properties, which do not apply or do not work under the framework of fuzzy logic. One of such, properties is what is called locality. Okay. So in a logical system, if we have the rule that A implies B, then we can conclude B if A is given without worrying about anything else. So if we know that A implies B and if we know that A is true, then B must also be true. And that's all. We don't have to know anything else. But when we have a probabilistic system, and even in the case of a fuzzy system, then all the evidences must be collected because A implies B, also has a certain probability of being true. It is not always true. And so, in probabilistic theory and as well as fuzzy systems, the concept of locality no longer holds. Then you have this concept called detachment. So what this says is that if we are able to find a logical proof for a proposition B, then that proposition can be used without worrying about how it was derived. And that is detachment of the proposition from its justification. So once a particular proposition has been found, you can detach it from its justification and you can use this given proposition in any future inferencing procedure without worrying about how it was derived. However, when you again deal with probabilistic systems or systems of fuzzy logic, you have to worry about the source of the evidence, and that plays an important role in subsequent reasoning. So again, this concept of detachment is not exactly valid when it comes to systems where this binary categorization into true and false is not easy. Then another property of these rule-based methods is what is called truth functionality. And what it says is that if you have a complex sentence which is made up of various components, and if you know the truth value of the components, you can very easily compute the truth value of the complex sentence. But again, when you have probabilistic systems or fuzzy systems, then it does not really work this way because you need to understand the relationships and the correlations between the different components. So unless you have a strong global independence assumption, in that case you can still work out the truth value of the complex sentence fairly easily. But in most practical situations, this global independence assumption doesn't really work. And so the simple way of constructing the truth value of a complex sentence from its individual components doesn't really work when it comes to probability theory or fuzzy logic. So now, to give an example of why is it that we need to extend our first order logic to a system of fuzziness, let's take this example. And this is a paradox which is called the Barber of Seville. So you have a small town in Spain, and the rule in that town is that all and only those men who do not shave themselves, they are shaved by the barber. Okay, so there is a barber in the town, and all the men and who do not shave themselves, they are shaved by the barber, and men who shave themselves, they are not shaved by the barber. So the question is, who shaves the barber? Now this is a paradox, because if the barber shaves himself, then he cannot be shaved by the barber going by this condition, and if he does not shave himself, then he must be shaved by the barber. So either ways you get into a contradiction, and what can be shown is that this is because first order logic or propositional logic is a binary system, that either the barber shaves himself or the barber does not shave himself, and that is what is leading to the contradiction. So if we relax that constraint that our truth value need not be binary in nature, this paradox can be resolved. So let's see how do we do it in fuzzy logic. So we have this proposition that the barber shaves himself, and let us call it S. Okay, and so not S is the proposition that the barber does not shave himself. Okay, so S is the proposition that the barber shaves himself, and not S is the proposition that he does not shave himself. So what we know from the paradox is that if S is true, then not S must be true, because if S is true means the proposition that the barber shaves himself, then he should not be shaved by the barber. And if not S is true, then that implies that S must be true. So this is clearly a paradox, So we can just hang on a bit, don't have to, make a judgment, right now. So just apply, whatever rules of first order logic, that are allowed over here. So we know that in first order logic or even in propositional logic, that if alpha implies beta and beta implies alpha, then alpha and beta are logically equivalent to each other. So here in this case, S and not S are logically equivalent to each other, which means that their truth value is the same. The truth value of S and the truth value of not S is the same. And we know that the truth value of not S is 1 minus T of S. So solving this, we get T of S equal to 1 by 2. So this looks like blasphemy. How can the truth value of a statement be half? But fuzzy logic is, kind of okay with it, that there can be situations in life when the truth value need not be 1 or 0, but it can be somewhere 50-50. So this is what fuzzy logic provides, and it is very useful in applications which we are going to see later on. So basically you have this idea of a membership function in fuzzy logic, which is not just a binary thing. So let's say if we talk about a classical set, which is also called a crisp set, in that case either a particular element belongs to the set or it does not belong to the set. So that is defined by this classical set A membership function, which is this gray line. So it is, the gray line is 0 for some values of x, then it becomes 1, and then it again becomes 0, which means that all the values of x in this range belong to the set, and all the values of x outside this range do not belong to the set. So that's a classical or a crisp set, that an element either belongs to the set or it does not belong to the set. In contrast, we have what is called a fuzzy set, where the membership of the elements is not binary, meaning that whether a particular value of x belongs to the set or not has a fuzziness, that it belongs roughly 30% of the times, kind of. So this is what is significantly different from between what is a classical set and what is a fuzzy set. So let's take a more concrete example to understand. So let's say there are these several people and they have certain heights. These are again random numbers. There's nothing, these numbers do not really hold any meaning. That just that they have been randomly assigned to these people. So if we, let's say, had a, a certain set where we want to identify which of these members are tall. So if I want to have a crisp set of people who are tall, then I can say that I put a cutoff at 190, and if the height is above 190, then they belong to the set. If the height is below 190, then they do not belong to the set. As simple as that. Now this is okay. This works well in many situations, but there are many other situations where this does not work well, and there you need to have a fuzzy description of the membership. And so what you will say is that if my height is far below 190, then the membership will be close to 0. But as my height starts nearing 190, the membership of the particular element in my set will keep increasing, and then as the height increases further, it will saturate to a value of 1. To show it pictorially, I have this membership function. So this gray step function is the membership function for my crisp set, where I have a cutoff at 190. Below 190 it does not belong to the set. Above 190 it belongs to the set. In contrast, the red curve shows the fuzzy set, where the membership in my set is not a simple 1 or 0, but something that changes smoothly from 0 to 1 as I change the parameter value. So this can be represented in this way, that you have the truth value for a particular element u, which belongs to my universal set capital U, and it can take any value between 0 to 1. Okay. So the truth value for my proposition P is my membership function with the variable x, where this membership function value can be anywhere from 0 to 1. So what this indicates is that the degree of truth for the proposition P, which is x belongs to A, is equal to the membership grade of x in the fuzzy set A. But remember, very, very importantly, that degree of truth is not equivalent to probability. Again, emphasizing on this because it can be confusing. So probability means that the set actually, is binary, that the member actually belongs, the particular element either belongs to the set or does not belong to the set. And probability comes in because of my ignorance, because I do not know what the right answer is, so I am guessing that okay, maybe it belongs here, maybe it does not belong. In fuzzy set, the membership is inherently not binary. Okay, so I'm not saying that because of my ignorance I do not know whether it belongs or doesn't belong, so I'm assigning it some value, but I'm saying that inherently it is a non-binary description. Okay, and that is how I get my degree of truth, that it belongs there with a certain fraction of membership instead of it being 0 to 1. We'll see an example which will make this more clear. So how do we apply these various logical operators actually in a very similar way to how we do it in first order logic, but there are some minor differences in the actual implementation. So let's say we have disjunction, which is P or Q, which means x belongs to A or x belongs to B, and that is simply computed by using the max function. So the truth value of P or Q will be the maximum out of the truth of P or truth of Q. Whichever is the maximum out of these two will be the truth value of P or Q. You can see that this applies to the binary case also. If let's say T of P and T of Q can either be 1 or 0, then when P is 1 or Q is 0, then truth value is 1, and the only condition when this can be 0 is when both T of P and T of Q are 0. So this relation that we have written over here holds true even in the binary case of first order logic. Then we have conjunction, where we have P and Q to signify that my element X belongs to the set A and also it belongs to the set B. And this truth value of P and Q is the minimum of T of P and T of Q. And this again you can verify that this holds true even in the case of first order logic. Then we have negation, that if my truth value of P is 1, then obviously my truth value of P bar is 0, and if TP is 0, then TP bar is 1. So in general, T of P bar is equal to 1 minus T of P, which again holds true in first order logic. Implication, that we know already, that P implies Q. This can be written as X does not belong to A or X belongs to B. And so the truth value of P implies Q is the truth value of not P or Q. This is just the or written in the form of a union. And we already know how to compute the truth value of disjunction. Okay. And then finally we have equivalence, P equivalent to Q. So the truth value of P equivalent to Q is 1 or 0. It is 1 when T of P is equal to T of Q, and it is 0 when T of P is not equal to T of Q. Okay. So these are some very simple ways of computing the truth value of various propositions in fuzzy logic. So now let's see how do you do inference, by using some of these ideas. So the slides that I am going to use for this fuzzy inference were taken from this particular link, which you can also refer to if you feel necessary. So let's take a particular problem where we have the weight of a person and the height of a person. So what we say is that if the weight of a person is, let's say, below this quantity, then we will call the person to be very slim. But it is not a binary membership, that it's not that if it is below this threshold then the person becomes very slim with a membership function value of 1. No. As you go towards the left hand side from this point, the membership in the set called very slim increases and it becomes 1 only after a particular threshold, because very slim is a English term which does not have a very precise meaning or definition. So what we are using over here is some kind of a commonsensical meaning or representation of the set very slim. Similarly, what we call slim is not something very, very precise, but something that is slightly vague, slightly fuzzy. So if let's say your weight is at somewhere over here and it increases, then you slowly start moving in the slim category. In this range you are definitely slim, and then as the weight increases beyond a point, the your membership in the slim set again keeps decreasing and it becomes 0 over here. Similarly for medium weight, heavy weight and very heavy weight. You can do the same thing for fuzzification of height, that if you are, let's say, below this threshold, then your membership in the very short category increases till it reaches saturation at 1. Then in this range for height you will be called short. In this range you will be called medium. After this height you will slowly start losing membership in the medium set, and finally your membership in the medium set will become 0, and here you will be a member of the set which is tall, and again as you move towards the right you get into the very tall set also. Now using the weight and the height, we can now compute whether the particular person will be unhealthy, less healthy, somewhat healthy or healthy. Okay. So what we are going to do is that we are going to take a particular value for the height and the weight, and we will see how can we use fuzzy logic to determine that whether the person is in one of these four categories of unhealthy, less healthy, somewhat healthy, and healthy. Okay, so what this particular diagram means over here, that we will see little later on, because this may not be very clear to you, but just for the sake of saying something, so there is some parameter value on the x-axis. If that parameter value is on the lower side, then you will be unhealthy. But here also again the membership is not binary, but in a triangular form, and as the value of the parameter increases, you move from being in the unhealthy category to being in the healthy category. So now this matrix shows you how the various categories for height and weight relate to each other. So let's say your height is very short and you are also slim, then you are in the slightly healthy category or the somewhat healthy category. If you are very short and if you are heavy, then you are definitely unhealthy. If you are, let's say, tall and if your weight is medium, then you are healthy. And similarly, you can identify whether you are less healthy or unhealthy by using this matrix if you know the height and the weight of a person. But as we know from here that the membership of a person in the slim or the medium or the tall categories is not something that is binary. So that is what complicates the situation, and that is why we need to follow a certain procedure to identify the membership in a precise manner. So let's take these values as a example, that the weight is 49 kgs and the height is 185 centimeters, and we need to identify whether the person is healthy or unhealthy. So let's take the weight function first. So the weight is 49 kg, so it will be somewhere over here just before the 50 kg mark, and if we draw a vertical line, what we will find is that it intersects with the slim category and the very slim category, and the values at the intersection point on the y-axis are 0.2 for the slim category and 0.8 for the very slim category. So we can say that the membership function from the weight perspective in the very slim category is 0.8 and in the slim category is 0.2. The membership for the remaining three categories of medium, heavy and very heavy are 0, because at 49 there is no intersection with these three curves. Now let's take the height set. You have height to be 185 centimeters. So we draw a vertical line at 185 centimeters and we find it intersects with tall and medium, and the values in the y-axis are 0.3 for tall and 0.7 for medium, and of course it is 0 for very short, short and very tall. So now we will use these membership function values and see how we can infer using fuzzy logic whether the person is healthy, somewhat healthy, less healthy or unhealthy. So this is again our matrix which I had showed you earlier, and these are the values for our membership function. So what we can do is that, so now for very slim we have 0.8, so we have written 0.8 over here. For slim we have 0.2, so we have written 0.2 over here. For tall we have 0.3, and that's why we have written 0.3 over here. And then for medium we have 0.7, and that's why in place of medium we have written 0.7 over here. So there are these two rows that are of interest to us and these two columns, and their the intersection point is this 2 cross 2 portion of the full matrix. So now what do we do? So what we do is that this is a and function, that the height of the person is 185 and the weight is 49. And we know that when we are doing and finding a truth value, we need to take the minimum of the individual membership function values. So in place of, so the weightage of LH will be a minimum of 0.7 and 0.8. Okay, so what we need to find over here is that what is the weightage or what is the membership function value for the set LH. And what is that? It is the membership function of medium and the membership function of very slim. And we know that when we do an and in fuzzy logic, we need to take the minimum. So here in place of LH, we will have 0.7. Similarly, for H, we have the membership function of height is 0.7, for weight is 0.2. So here also we will have 0.2, which is a minimum of these two. In place of U, we will have 0.3. In place of SH, we will have 0.2. And that is what we get over here by taking the minimum of the values in the height and the weight. And again, remember that this comes from the AND operator, which is calculated using the min in fuzzy logic. And for all the other cells, we have 0 because here we do not have any intersection of the height and the weight cells. So now we have the weightages of the 4 categories. So we have LH, we have H, we have U, and we have SH, and all of these now have their own weightage functions. So now what we do, we take the original function, the graph that we had for the different categories, and we scale that using these numbers. So the unhealthy graph, we scale it by 0.3. The less healthy one, we scale by 0.7. That's why it is so tall. The somewhat healthy one, we scale it by 0.2. And the healthy one, we scale it by 0.2 because that is what we have over here. So now what we need to do is that we need to find the centroid of this graph. Okay, when we find the centroid, we get that the D point, the value is 0.4429, which is somewhere over here. When we draw a vertical line, we find that it intersects with less healthy and somewhat healthy, and the values on the y-axis are 0.25 for somewhat healthy and 0.75 for less healthy. And so now our fuzzy decision index, we can, by using the fuzzy decision index, we can say that this particular person with a weight of 49 kgs and a height of 185 kgs is 75% in the less healthy group and 25% in the somewhat healthy group. Now again, remember this non-binary membership in a set is not because of our lack of knowledge or because of our ignorance, but because of the inherent ambiguity in the definition of these sets, which is unavoidable in many practical situations. So this was a very simple introduction to fuzzy logic and an example of how you can do inferences using the fuzzification and the defuzzification process. So here this is the defuzzification process where we have gone back from these graphs to getting the actual membership value. Thank you.